Okay, number 8, find the volume of the solid obtained by rotating the region bounded by y equals x squared, y equals 0, x equals 1, x equals 2, about the line, x equals 2. That looks like the exact same problem we had on number 5. Same equations at least to create the region. So if I just reconstruct that really quickly. So y equals 0, x equals 1, put that there. X equals 2, put that there. Y equals x squared, so 1, 2, 3, 4. So 1, 1, and 2, 4 would be y equals x squared, those 2 points there. X equals 1, x equals 2, y equals 0, there's my region. Now this time the axis of rotation, what makes this problem different than problem number 5 is axis of rotation is the line x equals 2. So my axis of rotation is right here, so the mirror image is going to go off like so, like here. Now I could do either method here, cylindrical shell method or the disk method. The disadvantage to the disk method here is that it had to be 2 pieces. So I'd have everything above this dotted line is based on an outside radius of whatever this curve is, and with all this stuff going on. And then this outside radius never changes on this little bit here. So basically I have this cylinder with this like weird like circus tent looking feature on top of it. The advantages to the cylindrical shell method, that's what I'm going to use, is I just have to make a cylinder and it never changes. So if I make my cylinder, it doesn't matter that it goes off to this area over here at the end, it figures itself out. So I draw my cylinder inside my region, my height's inside, and again I pretend there's an invisible side back there we can't see. My height is always within the region, and my radius is always from the axis of rotation to the curve that I'm dealing with. Notice that the height is coming off the x-axis straight up to the curve, so the height equals y. But the radius is coming from the axis of rotation to the curve, not from the y-axis to the curve. So this is x, this is r is not x. From here to here is 2. So we can see that r plus x equals 2, so r is equal to 2 minus x. The other thing I can see here is my radius is growing horizontally, and since my radius is growing horizontally, I'm concerned with a dx integral. And on top of that, my region starts at 1 and ends at 2. That's my interval. So again, if I'm using the cylindrical shell method, whether it's the last problem or this one, where the region lives 0 to 4, that was the interval. The region is from 1 to 2, that's the interval. All right? I need everything to be about x, so the radius is fine the way it is. The dx and the interval for x is all good. This is not any good. So h equals y. Y equals this curve here, which is y equals x squared. So height is equal to x squared. Now I got my height in terms of x, my radius in terms of x, I've got my interval in terms of x, so my volume is 2 pi RH. I'm integrating the RH part of it, 2 minus x times x squared dx. And my interval goes from 1 to 2. Distribute the x squared, I'm going to get 2x squared minus x cubed dx. And then I simply integrate that. Power rule for both. I'm just going to get 2x cubed over 3 minus x to the 4th over 4 from 1 to 2. If I put 2 in, I'm going to get 8 times 2, so 16 over 3. Put 2 in here, I'm going to get minus 16 over 4, better known as 4. Put 1 in, I'm going to get 2/3. Put 1 in there, I'm going to get minus 1/4. Common denominator of all that is 12. So times 4 makes 64. Times 12 minus 48. Distribute the minus and modify the denominators. Times 4 minus 8. Times 3 would be plus 3. And then if I just combine like terms on top, 64 minus 48 is 16, 16 minus 8 is 8, 8 plus 3 is 11. And then the 2 chops the 12 down to a 6, so we get 11 pi over 6 cubic units.